Hey all, this is going to be a quick video introducing the idea of slope. We're going to look at slope from about three different directions. One, given 2 points, finding the slope between them. Two is calculating slope from a table, which is basically the same thing as one. It's just the information is given a little bit differently. And then the third would be finding the slope from a graph, which we could do using points, but there's actually an easier way to do that as well. Slope is defined as the vertical change over the horizontal change. And you might remember from a previous class the words rise over run. So we're figuring out how far something travels horizontally to how far it travels vertically. Sometimes you'll see that written delta y, delta x, and delta just means change in, is what math folks use that little symbol for. And then a couple other words that they use interchangeably with slope is rate or average rate of change. And so we may see that in some of the problems. In terms of algebra, this formula right here is kind of the workhorse, where we do the slope, which is denoted with the letter m, is, if we think of this as two coordinates, it's the change in y2 minus y1, over the change in x2 minus x1 of those 2 points. And I'll show you this right here with this example. So, given 2 points, we'll use the slope formula to find our slope. It doesn't matter which point you call the ones and which point you call the twos, but what is important is that once you call this one x1, that you call that one y1, and that you don't get those mixed up. So let me get my pen set up here. So let's call this point x1 and y1, and we'll call this point x2 and, oops, very good, y2. And so then plugging into this formula, we're going to find our change in y, so that will go m equals minus 10, y2 minus y1 minus 15. So there's our change in y over x2 minus x1, so that would be negative 12 minus 10. And with the minuses in these, be careful that these two minuses always make it in there. If this had been, say, a negative 15, just for instance, we'd want to be careful to write minus 10 minus a negative 15 and make sure that we keep the minus from the formula because it's the difference between the points, and then we don't lose the sign on the point as well. So just that little spot is where people make a lot of sign errors. Continuing over here, minus 10 minus another 15 would be minus 25, and minus 12 minus 10 would be negative 22. And since we have a double negative right there, we'll rewrite that as a positive, because a negative divided by a negative is a positive. 25 is 5 times 5, nothing to reduce with this 22 down here, that's 2 times an 11, and so that's how we would leave this. Typically you don't want to change to a decimal, you want to just leave this as an improper fraction that's as reduced as it can be. So for this one, that's about as far as we would be able to go. For this next example, what's the rate of change, which is, again, another word for slope. For this function, what are the units of the slope? So same idea, it's just now we're looking at this in the form of a table rather than to order 2 points. We can rewrite those as ordered pair if we like. I'll just arbitrarily grab these first 2 points. And we'll do 2 and 89. And then it's basically the same thing as the last problem. So for this we would say m equals 89 minus 100 and over 2 minus 0. And that's going to be negative 11 over 2. And then it asks for what are the units, so we come back to our table here, and it looks like our output is in miles. And then our input, our change in x is in hours. And so this is negative 11 miles per every 2 hours. If that sounds odd, and again, we don't generally want to switch this to a decimal, but for the sake of kind of making sense of these units, let me do that for a second. This would be saying negative 5.5 miles per hour. per 1 hour if we wanted to write it that way. Again, this is perfectly good and a great place to stop, but the negative 11 over 2 seems a bit awkward when we're speaking of units. And if anyone's thinking, how do you go negative 11 miles? Distance is a vector quantity, and so if I thought of this as west and this as east, and it's starting right there at 0, this means we would be traveling in that direction. 5.5 miles for every 1 hour would be one way to interpret that. For number 8, same basic thing. Let's see. So the table below gives annual sales in millions. What is the average rate of change, again, slope of annual sales between, and this time they gave us a specific range to look at. For this one, all of these points were equal distance apart, and the slope would have been the same no matter where we looked. For this one, it isn't. So they're asking, what is the average rate of change in annual sales between 1998 and 2003? So let's see, for 1998, that goes with 116. And 2003 is right there, and that goes with 241. Oops, that's not a very good one. And so we can calculate that. So M would equal 241 minus 116, and then that's over 2003 minus 1998. And we throw that in the calculator, and that came out to 125. That is 5 years apart. So 5 into 125 would be 25. And if we wanted units, this would be in millions per year. So in this case, the sales increased by 25 million per year on average between those 5 years. Same thing, this has a few words this time instead of a table. So city's population in 1951 was that much, in 1968 it was that much. Compute the slope and then choose which statement is most accurate. So for here we would have, let me scroll that up, M equals, we'll use this as our x1, y1, and this one is our x2, y2. So 1716, 0, oops, that's an 8, 0, 0. Subtracting this one. And that's going to be 1968 minus 1951. And throwing that in a calculator, we get negative 6,800 over 17. And that would reduce down to negative 400. So negative 400, if we try to interpret that, that means the population would be decreasing by 400. This was people up here, and this is years. So negative 400 would mean the population is decreasing by 400 people per year, and looks like that is right there, that one. Oops. And then lastly, we can find slope from given some lines on a graph. And we can do this a couple of ways. We can take 2 points, it doesn't really matter where. I always look for places where it's intersecting. So like that would be a good one, that would be a good one, that would be a good one. You kind of want the spots where it's crossing on easy places to count. And so I could write out these ordered pair, and I'll see people do that where they'll write out the point 2, negative 2, and 0, 3, and then go through and calculate it. But a much easier way to do that is to just count the boxes. So if you look right here, our run in this case would be 2, our rise in that case would be 1, and so our slope, oops, come back, is going to be rise over run, so m would be 1/2. It's change in y over change in x. So to me, that's a much easier way to do that than to grind out the fraction version using the slope formula. For this one, let's see, that looks like a good point. And we'll just keep going down until we find another spot where it intersects nice and clean. And so this one looks like my run is 2 and my rise is, and now notice for this one, as I go to the right, it drops down, so that would be a -3. If the function of the line is increasing, it's getting bigger as we travel left to right. That would be a positive slope. Where it's decreasing as we travel left to right, that would be a negative slope. So here this would be m equals our rise, -3, over our run, which is 2. So in other words, for every 2 units I travel to the right, it drops down 3 units. And for this last example, let's see, there's a nice point there. No. There's, that one looks good right there. So this one, we're going to have a run of 2. It looks like our rise is 1, 2, 3, 4, 5 there. And again, being careful to notice that it's decreasing, so that's going to be a -5. So for that last example, it will be -5 for our rise, and 2 is our run. Hopefully that helped make some sense out of slope.